Hello, Akayum. Are you able to see the slides? And can you hear
Yes,
me?
sir.
Okay.
Yes, sir. Good afternoon, sir.
Good afternoon. So, in the meantime, let me show you. Let me share the. Have you gone through my YouTube channel?
Yes, sir. Yes, sir.
If not, then I'm sharing a link once again in the chats, so
Yes,
that
sir. Yes.
everybody can access it. And we are waiting for 3-4 more minutes. So,
Okay.
okay. So, by the time others are joining, uh, let's see like what sir is taught in the week 2 classes.
Okay, sir.
Okay, so if we see in the week 2 classes, in lecture 6, sir has given a recap of local time and local solar time, and all the angles like zenith angle, azimuthal angle, and solar altitude angle, incidence angle, and we have done many numericals about it also in the last class. Okay, sir has derived it geometrically and derived the formulas, and then just did some numericals over it, which we have already tried. And after that, the other class, sir has actually talked about the semiconductors. Okay, he has given a recap of the solar radiations, the components, and other things. Then he has talked about the conductors, semiconductors, and insulators, the differences between them, resistivity, conductivity, what makes them difference, how to calculate uh, their drift current, and all these things. Sir has talked about their band diagrams, everything sir has talked about. How do they differ? And how do we calculate the density of states, and on the basis of density of state how do we make them differ. And then in lecture 8 sir has talked about the energy band regions, like uh, anybody has joined, others are not joining today, huh? Anyways, so in lecture 8 sir has talked about the energy band diagrams, and how these energy band diagrams are differ for all these things, and how these and density of states uh, controls the, the application of these semiconductors uh, into various solar devices, and what are intrinsic semiconductors, what are extrinsic semiconductor, what is the difference between N and P type of semiconductors. All this sir has talked in this lecture number 8. And lecture number 9 sir has talked about the Fermi level and the Fermi energy from direct statistics, and how do we calculate it, and how these Fermi level guide us to select the material for using for solar photovoltaics. In lecture 10 sir has actually talked about the basics of solar photovoltaics, their principles, technologies, and materials, and some basic concepts, drift current, and this diffusion, all this mobility, carrier mobility, all these things, scattering and all, sir has talked about. So basically what I will be doing, I am first going to give you a little bit initial information, a recap of band theory of solids, differences in metals, insulators, and semiconductors on the basis of their bands, and the difference in intrinsic and extrinsic semiconductors. And then we have around 12 questions today, which we will be discussing on the basis of week 2 classes. So I'm waiting till 3:10 p.m. Let others join and then we can start.
Okay, sir.
So, Aquarium, what do you do? Like, what are you pursuing? Like, am I
Sir,
pronunciating your name right?
hello.
Yeah, yeah. You're audible. You're
Sir,
audible.
actually, I have enrolled in PhD in November
Okay.
2022
Okay. Where?
through AICT Doctoral Fellowship
Hmm.
at JC Bose University of Science and Technology, Faridabad.
Great. Great.
That is formerly known as YMCA University.
Yeah, YMCA. I know it.
Yes.
I have been to
Sir,
YMCA once.
okay, sir. Okay, sir.
Faridabad
Basically,
campus. I've been
sir,
there. Actually, let me tell you, I did my graduation from Delhi University. So I was from Deshbandhu College. So I have wandered there a lot. So I know all these areas.
okay, sir.
Yeah. Why
So
others
right
are not?
now,
Why
I'm
others are
going
not?
to only
What? What?
that is coursework. Coursework is going on
Hmm.
right now,
Hmm.
and after that, I will choose topic. My topic, broad topic is renewable energy.
Great.
So
So
if you have any, please suggest me what is the topic regarding renewable energy in
um,
photovoltaic
yeah,
or thermal energy.
they are the burning topics. You can see all the streams, like even it is organic, inorganic, physical, or even you can say, the physics, the physical sciences, all are jumping into this photovoltaic field. Why?
Yes, sir.
Because of the booming need of energy, and the booming need of energy can only be satisfied if we do research in the areas which are burning, and the burning areas are photocatalysis, CO2 reduction, water splitting, battery, and then perovskites, solar cells. These are the burning areas which are the actual form of renewable energies. So right now in the market, if you see, perovskites are very much famous and very much common. So a lot of people are working on perovskites.
But sir, there is a limitation at JC Bose University because there is no machinery regarding research.
No,
Then
I
how
completely, I
to?
completely, I completely understand. In that case, aquarium, I know the hardships, but in that case, what you can do, you can try to do the synthesis at your place. You can plan an idea. You can do collaboration, and if not doing collaborations, you can send your samples outside from your contingency for doing measurements. Like there are certain IITs or certain central universities or certain bodies, CSIR labs, which allow external student to send the samples for measurement by paying some money. So this is how you
Yes.
can help out. But once first you need to have a PI, you have to choose a PI, you have to make sure a field, you have to go through the literature survey for initial some months, then you start working. Okay, it's not like that on the very first day. PhD is a very different stuff than 11, 12 or bachelor's or masters. Okay,
Yes.
so here you have to devise an idea, you have to execute it,
Well,
you have to
basically,
write
I
it.
want to do research in the field of cooling a photovoltaic cell.
Oh, great, great, great.
Through this, I want to enhance because we know that when solar radiations falls onto the surface of the solar panel, only 10 to 20% will be converted into electricity,
Hmm,
and 70 to 80% will only going to heat up the solar panel,
hmm,
and it totally waste. Or due to this heating process, the solar efficiency and power output also decreases.
hmm.
Drastically changes as per literature review. We know that 1 degree centigrade, by increasing 1 degree centigrade temperature panel, there is a 0.5% efficiency decreases.
Absolutely right. But Koyum, let's see, there are three generations of solar cells. A lot of research has been already done in quantum dot sensitized solar cells. So before jumping onto the solar cells and solar photovoltaics, you need to understand like what are the first and second generations, what are quantum dots, how do you synthesize quantum dot, how do you tune these their properties, and how do they affect the property that you're talking about. I completely
Yes,
understand, and everybody is trying to increase the efficiency, minimize the losses of heat, and get more and more efficiency. But it is not so easy business. You getting me?
yes, yes, yes.
So you need to first of all understand the basics, the working idea, the device architecture, and when you will jump into the experimental thing, then you will come to know that whatever idea you are trying to implement, I'm not demotivating you. You may not get the results that you are planning for. So first of all,
Yes, yes.
clear out the basics. Okay, like your idea is appreciable. You should have motivation and mission to execute it, but clear out the basics. That is more important. Okay, so if others are not joining, Karam, I'm starting. Okay.
Okay, sir.
Okay. So, are you able to see my slides now?
No, sir.
Oh, okay. I'm not presented a screen. Now, are you able to see my slides?
Okay, sir. Yes, sir. Yes, sir.
Okay. So, not everybody is there. I hope other joins. But in the meantime, let me introduce myself again. I am Shresht Gupta. I'm a PMRF scholar at ISA Kolkata, and this is a second teaching assistantship class of a course Solar Photovoltaics, which is being taken by Professor Ashish Garg at IIT Kanpur. The YouTube channel link and the drive link I have already shared in the chat box, and after it, I will always be giving the PDF solution of all the assignment discussions. And even though if some doubt remains or I'm not able to satisfy any of your query, you're always free to email me afterward regarding any confusion, any concept, or any suggestions or any study matter you need in the same regard. Okay, so without any delaying further, let's go to some initial. Just a minute. I think my laptop is creating some issue. I'm sharing once again. Okay. So without any further, delaying further, let's see the bend theory of solids. I have taken this from NCRT. Okay, this has been taken from NCRT. This is a very basic concept, but we need to clarify it. Okay, so just for the sake, consider a silicon or a germanium crystal which has n number of atoms, and each atom has a discrete energy level, as we can see here. As we can see here, okay. Yeah. As we can see here. So in a crystal, the atoms are close to each other by 2 to 3 angstroms, and therefore the electrons also interact with each other. Now the point is ki how do we understand the energy, and what is the energy gap, and what is a band gap, and how do we call it a conduction band and a valence band. So suppose there are in atoms which starts coming nearer to each other, uh, to form a solid. The energies of these electrons in the outermost orbit may change due to the interaction between electron and different atoms. Okay, so still you can see that there are electrons, there are shells, and they are at different energy levels. As we have read in the chemistry classes in 12 class, that there are four types of quantum number, principal, azimuthal, and all this. You can see n is the number of shell, l is this, and they are the relative energies of the electrons. On the basis of their relative energies, there is some smaller spacing. Okay, they all don't have a identical energy, and when they all get mixed, there is an upper energy level and a lower energy level, and a distance between them further decreases. The energy band again split apart and separate by an energy band gap is called Eg. This is called the band gap. Okay, and which is completely filled is called the valence band, and the upper band is completely empty. The upper band is called the conduction band. So if I concise it once again, and on the basis of the energy levels, there are some discrete energy levels crystal has, and then there are bands which are which are formed due to the overlapping of different reasons, and one band has full of electron, one band have less of electron. The one which is having full of electrons is the upper band and is called the valence band. Valence band is completely filled and the upper band is completely empty, and the upper band is called the conduction band. The valence band and the conduction band. Okay, Akyum, you are able to understand? Just for the sake of example, what's happening?
Yes, yes.
I think some issues are happening in my laptop. Just a minute, Akyum. Okay. Okay. I don't know, my screen has locked. Hello Krishna, you're late. Why do you join so late? Krishna, my computer is hanged. Just a minute. Okay. So, Krishna, am I audible? Krishna, am I audible? You can type in the
Yes,
chat
sir.
box. Okay. So let's move further. I was discussing this actually, and but yeah. Are you able to see the screen, Krishna? Okay. So is my screen visible now, Krishna?
Yes, sir. Yes.
Okay. So we were discussing this, the band theory, how this conduction band and the valence band concept come, and how these metals, insulators, and semiconductors are different. So we just now I was discussing with Aquam that how this conduction band and the valence band forms, and then how the concept of this metals, insulators, and semiconductors come into picture. So this is taken from the NCRT book, Krishna. The first and second are the metals where we can see that there is not much energy gap in between the conduction band and the valence band. Eg is nearly equal to 0. But there is a band gap when the band gap is greater than 3 electron volt and the conduction band is nearly empty, then they are called insulators in general language, in a layman language. And when the conduction band and valence band there is a energy gap less than 3 electron volt, that means the electron can hop over to the conduction band, not like metals, but they can do, then they are called as semiconductors. Okay, the one more concept that I want to revive before going to the assignment questions. So the concept is the difference in between intrinsic and extrinsic semiconductors. So the basis of comparison that I have decided to explain is on the basis of impurity that are present, the electrical conductivity, the density of charge carriers, the dependency of electrical conductivity, position of the Fermi level, and their examples. So if we talk about the intrinsic semiconductors are pure forms of semiconductors, hence they do not have a significant amount of impurity. Extrinsic semiconductors are made by adding some impurity to the pure form of semiconductors. Somebody is trying to join. Yes. Okay, and the density of charge carriers, on the basis of density of charge carriers in the intrinsic semiconductor, the number of free electrons in the conduction band is equal to the number of holes in the valence band. And in extrinsic semiconductors, the number of electrons and holes are not equal. In extrinsic semiconductor, it depends on the type of extrinsic semiconductor. If we talk about the position of Fermi level in intrinsic semiconductors, the Fermi energy level lie in the middle of the valence band and the conduction band. But in extrinsic semiconductor, the Fermi level shifts towards the balance of the conduction band. Example of intrinsic semiconductors are pure silicon or germanium, and extrinsic semiconductors are silicon and germanium crystal with impurity atoms like asbestos, antimony, P, or indium, boron, and aluminum. Now extrinsic are also of two types, N and P, on the basis of impurity that are present there. If a trivalent impurity is present, that means there is a hole, and if a pentavalent impurity is present, that means there is a extra electron. On the basis of that, they are considered as either N-type semiconductor, extrinsic semiconductor, or P-type extrinsic semiconductor. Okay. So if I move further, okay. So are you able to see my screen? Naresh?
Yes, yes.
Okay, so let's start with the questions now. So you have joined later. Let me tell you once more that I have this prepared 12 questions on the basis of week 2 classes for this assignment 2, and this is my YouTube channel link, and this is a drive link for the backup videos. And we have discussed about the band theory of solids, how this conduction band and valence band comes into the picture, and then how do we differ metals, insulators, and semiconductors on the basis of conduction band, and then how these semiconductors can be classified as intrinsic as well as extrinsic on the basis of on the basis of doping and all these extrinsic semiconductor can further be classified into N type or P type. Now let's go to questions. I have given the revive overview so that you guys can correlate. Now the first question is key. What will be the whole concentration in centimeter cube in silicon sample maintained at 300 Kelvin with electron concentration of 10 raised to power 6 centimeter cube under equilibrium conditions, and the intrinsic carrier concentration Ni is equals to 10 raised to 10 centimeter cube. And the options are A 10 raised to 14, B 10 raised to 12, C 10 raised to 20, and D 10 raised to 6. And you have 3 minutes to give the plausible answer if you can solve this question, and if not, then I'll tell. Don't worry about it. You can type in the chat box if you know the answer. As nobody is there, I am trying to give the answer myself. So that if anybody of you sees a confusion later, you can further see it. So the answer is as follows. As we can see in assignment 2, the question was that what will be the whole concentration in centimeter cube in silicon sample maintained at 300 Kelvin with electron concentration of 10 raised to power 6 per centimeter cube under equilibrium conditions. We know we know that in a semiconductor the majority carrier electron concentration is n naught is equals to 1 over 2 nd minus na plus nd minus na whole square plus 4 ni square is to 1 by 2. Now from here we can see the electron concentration is 10 raised to 6, that means 10 raised to 6 per centimeter cube is the electron concentration, and they are asking about the whole concentration in silicon sample at 300 Kelvin. So the minority carrier whole concentration can be calculated as P naught is equals to Ni square over N naught, that is 10 is to 10 ka whole square over 10 is to 6, that means it will become 10 is to 20 over 10 is to 6, that means 10 is to 14. That's why the correct answer of this question is the A option, that is 10 is to 14. And we have further question like this in assignment 2 also. Now let's go to the next question. The next question is saying in a p-type semiconductor at 300 Kelvin, the accepted density is 10 raised to 17 centimeter per cube inverse, while intrinsic carrier concentration is 10 raised to 10 centimeter per inverse cube. So the position of the Fermi level of the semiconductor will be at, the options are A 0.417 electron volt below intrinsic Fermi level, B 0.357 electron volt above intrinsic Fermi level, C 0.417 electron volt above intrinsic Fermi level, D 0.259 electron volt intrinsic Fermi level. And you have 2 minutes to see, tell the answer if anybody is there. Else not, then I'll myself tell the answer. As nobody is here, so without further delaying, let me tell the answer so that you guys can see it later. So the question number 2 was saying in a p-type semiconductor at 300 Kelvin, the accepted density is 10 raised to power 17 centimeter cube inverse, while intrinsic carrier concentration is 10 raised to 10 centimeter cube inverse. The position of the Fermi level, let me have a check if the video is recording or not. Yeah, it is getting recording. So centimeter cube, the position of the Fermi level of the semiconductor will be at. That means we have given a p-type semiconductor, and we have given the accepted density as 10 raised to power 17 centimeter cube inverse, while intrinsic carrier concentration is 10 raised to power 10 centimeter cube inverse. Now they are asking the Fermi level. We know the from the formula that sir has told in lecture 7th and lecture 8, that the Fermi level position we can get by this formula: EF minus EI over Q is equals to 0.0259 ln Na over Ni. Okay, this is the Fermi level of the semiconductor, the position. So we know that Na over Ni, so this will be 0.0259 ln 10 is to power 16 over 10 is to power 10. That means 0.0259 into 16.12. That means 0.417 electron volt. That means the correct answer is 0.417 electron volt below the intrinsic Fermi level. Okay. Now let's move to the next question. The next question is question number 3. Question number 3 is saying that the resistivity of an intrinsic semiconductor is 6 ohm meter at 300 Kelvin and 3 ohm meter at 350 Kelvin. The energy band gap in electron volt of the semiconductor is, options are A 0.225, V 0.105, C 0.331 and D 0.169. Okay. So as nobody is here, let me tell the answer myself. Okay. So the answer is the resistivity is given as 6 ohm meter at 300 Kelvin and 3 ohm meter at 350 Kelvin. So the energy of the band gap will be explanation is like this. We know the resistivity formula that Eg over 2k 1 by T1 minus 1 by T2 is equal to ln rho 1 by rho 2 plus 3 by 2 T1 over T2. Rho 1 and rho 2 are resistivity. We put the values here, and after putting all the values in the respective temperature, that is 300 Kelvin, 350 Kelvin, and the Boltzmann constant and the rho 1, rho 2 and the T1, T2 value here, we get Eg is equal to 0.2711 cross 10 raised to power minus 19 joule, and then we convert this joule into electron volt. You know how do we calculate it? That is dividing by the charge of an electron, and then this comes as 0.169 electron volt. So this is the right answer. The next question is saying that which of the following are used to measure the solar radiations, and the options are heliometer, anemometer, thermistors, and pyranometer. This is a theoretical question and mathematical question. The correct answers are of these questions are that the heliometer and pyranometer, they both are used to measure the solar radiations. Okay, let's move to the next question now. The next question is saying that which of the following dopants are not suitable for making an extrinsic semiconductor. The options are arsenic, antimony, copper, and indium. Anybody is there to answer the question? Nobody is there, so let me do it myself. The answer is like this. We can see that in order to make an extrinsic semiconductor, keeping in mind the basic condition, the correct answers are copper and indium. We can see from the extrinsic semiconductors, acceptors impurity should create a hole or should contain a free electron, and in that case only two atoms among these four are can be used as a dopant in extrinsic semiconductor, but not arsenic or antimony, because they are themselves this having this kind of behavior. Okay, because they both have four electrons in silicon and germanium. This question number 6 is actually a theoretical question. So in question number 6 I am saying that the Fermi level EF determines the electron and hole concentrations of a semiconductor in equilibrium. Out of equilibrium we can define the quasi Fermi level EFN and EFP to calculate the electron and hole concentrations respectively. For example, the electron concentrations would be n is equals to nc exponential minus ec by minus efn over kt. Then we have to prove that a total electron current can be written as Jn is equals to mu n and defn over dx. Okay, so without delaying further, let's go to the solution. The solution is like this. We very well know that yeah, the electron current is usually written as an addition of its drift and diffusion terms. So the terms becomes like Jn is equals to q and mu and e plus q dn over dx. So the electron current is usually written as addition of its drift and diffusion terms Jn, Qn, mu and E plus Q dn over dx, where Q is the elementary charge, mu is the electron mobility in centimeter square per volt per second, E is the electric field in volt per centimeter, and dn is the electron diffusion constant in centimeter square per second. By introducing the electron quasi-Fermi level, we can write the derivative as dn over dx as dn over dx is equals to nc bracket minus 1 over kt dec over dx minus defn over dx exponential minus ec over efn kt. Dn over dx is equals to minus n kt minus q dv over dx minus defn dx is equals to minus n kt bracket qe minus defn dx. Now we have used that dec is equals to minus q dv. The band energy changes with the electrostatic potential, but the electron charge is minus q. So we have also used that E is equals to minus dv over dx. Now we use this last expression of dn over dx in the equation of the total current density. That is Jn is equals to Qn mu n Fe minus Q dn n over kt bracket Qe minus de Fn over dx. Now considering the Einstein relation, that is dn is equals to kt over Q mu n, we finally arrive to Jn is equals to mu n and de Fn over dx. This question was not of your standard, but this expression you should remember. This expression generally comes directly in numerical format, and it can help you in future. Okay, this is a very good question actually. Nobody is here. It's okay. So I will upload the recording and you can see it later. Okay, so let's discuss the next question. The next question is saying that we take a multimeter measuring in the voltmeter DC mode, and the red probe is heated externally, okay, with a lighter, while a black probe remains at room temperature. Then we contact on a silicon sample with two probes close to each other as shown in the figure. The heat transfer establishes uh, a temperature gradient in a semiconductor. The reading on the voltmeter voltage at the red probe minus voltage at the black probe is negative. With this information, could you determine if the sample is P or N? We know what are N type semiconductor, what are P type semiconductor. Now we are having all this information, that there is a voltmeter in a DC mode, the red probe is heated externally, and black probe is at the room temperature, and it is in contact with a silicon sample with two probes close to each other. The heat transfer establishes a temperature gradient in the semiconductor, and reading on the voltmeter is negative. With this information, can we really determine if the sample is P or N? The answer is as follows. We know that, let's consider first an n-type semiconductor. Because of the temperature gradient, there will be a net flow of the hotter electrons towards the cold sides. That is from near the red probe towards the black one. In open circuit voltmeter DC mode, and an electric field appears to cancel this current, which is oriented from the red probe towards the black one. Therefore, as the multimeter measures the voltage at the end at the red probe minus the voltage at the black probe, the reading would be positive. However, the image shows a negative value, and we conclude that the semiconductor is actually P type. Are you getting it? Because of this negative value, the semiconductor is P type. This is some experimental question. Now let's go to the question number 8. The question number 8 is saying find the built-in potential for a PN silicon junction at room temperature. If the bulk resistivity of silicon is 1 ohm centimeter, electron mobility in silicon at room temperature is 1400 centimeter square per mole per second, and mu n over mu p is equals to 3:1, and the intrinsic Ni is equals to 1.05 cross 10 is to 10 centimeter cube inverse. And the options are 0.68 volt, 0.68 electron volts, 6.8 volt, and 68 milli electron volts. I guess nobody is there in the call. Whoever is seeing this video afterward, I just suggest you all, I just request you all that you guys should attend these classes. These classes are meant for discussions, for clearing out your doubts, and telling you, helping you how you can actually solve the problems. So let me show the answer of this question number 8. The question number 8 answer is like this. By definition we know that by definition we know that E psi d is equals to Fn minus Fv. Concentration of the free carriers are given by n is equals to Nc exponential minus Ez minus Fn over Kt, and P is equals to Nb exponential minus Fp over Kt. From here we get that E psi d is equals to Ez plus Kt ln n over Nc plus Kt ln P over Nv, which is equals to Eg plus KT ln NP NC over NB. Since Ni square is equals to NC NB exponential minus Eg by KT, we know this relation. From here we obtain the psi d is equals to KT over E ln NP over Ni square. Okay. Okay, so from here n equal to 1 over E rho mu n and P is equal to 1 over E rho mu P. Thus we finally get psi d is equal to 0.68 volt. Okay, from these equations psi d can be calculated. NP, Ni, KT and E we know. This it comes at 0.68 volt. If you further has any problem, you are free to write, email me anytime, or as you have not joined the class, you could have asked me in between, but I'll share the PDFs in the drive. You can see it afterward, the recording, and the video will also be uploaded on YouTube. You can see the video from there, or a backup video will there be also on the drive. You can see it from there also. Okay. So the question number 9. So the question number 9 is saying for a P plus N silicon junction with Nd is equals to 10 to the power 16 centimeter cube inverse. The breakdown voltage is 32 volt. Calculate the maximum electric field at the breakdown where epsilon silicon is equals to 11.9. And our options are 3 cross 10 is to power 5 volt per centimeter, 3 cross 10 is to power 5 volt per meter, 3 cross 10 is to power 5 millivolt per centimeter, and 3 cross 10 is to power 5 millivolt per meter. I will wait for 2 to 3 to 4 minutes for this answer here on myself, as nobody have joined, because when you are seeing this video later, you give a try. In the meantime, after 3 minutes it's 3:43. At 3:46 I'll tell you the answer, so that you can match it up. You have 3 minutes to answer this question. Question number 9. Okay, so let me tell the answer now. The width of the electron space charge region is given by W is equals to epsilon V over 2 pi E and D raised to 1 by 2, and all of them have their nominal names, which is being explained in the class by sir. So from here, putting all these values, we get the value of W as 2 micrometer. Now from here we get that the maximum electric field at the breakdown is E is equals to 4 pi E and D over epsilon W. Putting all these values in expression, we will find out that the correct answer is 3 cross 10 is to the power 5 volt per centimeter. That means the correct answer is A. Okay. Now let's move to the next question. The next question is question number 10, where they are saying that why are silicon and gallium arsenide being preferred materials for solar cells? Any guesses? Anybody is there? Krishna, Aquarium, anybody is there? Okay, if not, you can see the video afterwards. Let me tell you the answer. This is a very good and important question, and this should be clear to you in order to design and understand the materials. So, the question was why silicon and gallium arsenide are preferred over solar cells. Now, let us show the solar radiation spectrum which are received by us, which is shown as here. You can see the solar radiance versus H nu, and the maxima is around 1.5 electron volt. Now, what does it convey? The maxima is near 1.5 electron volt, and for photoexcitation, we know that the H nu should be greater than Eg. Okay, this band gap. Hence, the semiconductor with band gap which is nearly is equals to 1.5 electron volt or lower is likely to give a better solar conversion efficiency. I repeat myself, a semiconductor with band gap nearly equal to 1.5 electron volt or lower is likely to give better solar conversion efficiency. Silicon has band gap around 1.1 electron volt, while for gallium arsenide it is around 1.53 electron volt. In fact, gallium arsenide is better in spite of its higher band gap than silicon because of its relatively higher absorption coefficients, which is also very important and major factor. If we choose materials like CDS or CDSE, the band gap whose band gap is around 2.4 electron volt, we can use only the high energy component of the solar energy for photo conversion, and a significant part of energy will be of no use. So the question arises, why we do not use materials like lead sulfide which satisfy the condition H nu is greater than Eg. So where maxima is mu is the maxima corresponding to the solar radiation spectrum. Now the answer of this question is necessary to understand. Suppose if we consider PBS, if we do so, most of the solar radiation will be absorbed on the top layer of the solar cell and will not reach in or near the depletion region. For effective electron hole separation due to the junction field, we want the photo generation to occur in the junction region only. That is why these materials, the silicon and gallium arsenide, are the most preferred materials, and not every lower band gap material is a preferred material for solar cells. Okay. Now let's move to the next question. The next question is question number 11. Question number 11 is saying the number of silicon atoms per meter cube is 5 cross 10 raised to the power 28. This is doped simultaneously with 5 cross 10 raised to the power 22 atoms per meter cube of arsenic and 5 cross 10 raised to the power 20 per meter cube atoms of indium. Now we have to calculate the number of electron and holes given that Ni is equals to 1.5 cross 10 raised to the power 16 meter cube inverse, and we have to also tell is this material a n-type or a p-type material. I am giving you 2 to 3 minutes to think about the answer, and if not then I'll tell the answer myself at 3:52. As nobody is there, let me answer the question. Question number 11. So the number of silicon atoms per meter cube is 5 cross 10 is to the power 28. This is doped simultaneously with 5 cross 22 atoms per meter cube of arsenic and 5 cross 10 raised to power 20 per meter cube atoms of indium. We have to calculate the number of electron and holes, and along with that, given that the Ni is 1.5 cross 10 raised to power 16 meter cube inverse, is this material N type or P type? Now, first of all, we know the number of electron, which is 4.95 into 10 raised to power 22, and number of holes is 4. 4.75 cross 10 raised to the power 9. So this is N type, since Ne is greater than NH. For charge neutrality, this is Ne minus NH, that is Ne dot NH equal to Ni square. Solving this equation, we can say that Ne is equal to 1 over 2 Nd minus Na plus root of Nd minus Na whole square plus 4 Ni square. From here we can calculate the number of electron, and then we can see that the number of electrons are greater than number of holes. This is an N-type material. Now the last question of today's class is question number 12. It is saying that in a PN junction, just a minute, in a PN junction, how does the built-in potential BBI change when the temperature increases? And we can start by considering the Venn diagram and expected evolution of the Fermi level with temperature, assuming that the band gap does not change much with temperature. An explanation of this question is that we know that following the suggestion of the problem, the built-in potential can be calculated as QBBI is equals to Eg minus Ef minus Eb P side minus Ec minus Ef on N side, on both of the side, and then Eg is this. So we know that the Fermi level shifts towards the center of the gap when the temperature increases, then both Ef minus Eb P side and Ec minus Ef N side will increase with temperature. Consequently, the BBI value of the junction will be reduced. Thus, we can see from this diagram, this is Eb, this is Ef, that is the Fermi level, Ei and Ec. Now this is QBBI. When this is generating, this will be reduced. So Ec minus Ef will be on the N side, and this is like Ef minus Eb on the P side. So what will be the final result? The final result will be that the BBI value of the junctions will be reduced. Hello Rajiv. Rajiv, can you hear me?
Yes, good afternoon, Shesh.
Good afternoon, good afternoon. So, like, nobody was there else in the class.
Oh,
I am just giving you a quick flashback. The flashback is
okay,
like this: that although I will be sharing all the PDF and this YouTube channel link I have already shared, and you're always free
okay,
to email me. I have first of all discussed the general introduction of the band theories, how this conduction band and the balance band comes into the picture, and how on the basis of this conduction band and balance band we define metals, insulators and semiconductors. And then I have just given a quick review just for the understanding. Some people were there at that time actually, that what are the differences in between intrinsic and extrinsic semiconductors. And then I have tried to solve some questions. In these questions I have tried to calculate this number of hole concentrations, the position of Fermi level and the band gap, and some theoretical questions which can be the elements which could be suitable for doping. And there are some theoretical questions which are question number 7 also, question number 10th also, and 12th also. So if you are there, let me discuss question number 7 and 10th once more so that you can also understand. Are you there?
yes, yes, I'm there.
So let's see question number 7. Although I have already discussed, I'm just giving a quick review. So what they are saying, that we take a multimeter measuring in the voltmeter DC mode, okay? And there are two probes, we know. There is a red probe and there is a black probe. The red probe is heated externally with a lighter, while a black probe remains at room temperature. And now when we contact on a silicon sample with the two probes close to each other, the heat transfer establishes a temperature gradient in the semiconductor. The reading on the voltmeter is minus. With this information, could you determine if the sample is P or N? Can you determine, Rajiv, like with the reading that you are seeing, that the sample is N type or a P type? Any idea? Any guesses?
I think it is P type
How do you say it?
because it is negative.
Good, good, very good. Absolutely right. It's a very straightforward question. But because I have framed it in a different way, so let us see. I have given the explanations like this. So let us consider first an n-type semiconductor, Rajiv. Because of the temperature gradient, we know that there will be a net flow of the hotter electrons towards the cold side, and from the near the red probe towards the black one. Now, in an open circuit, that is in a DC mode, an electric field appears to cancel this current, which is oriented from the red probe towards the black one. Therefore, as a multimeter measures the voltage at the red probe minus the voltage at the black probe, the reading would be positive. However, the image shows a negative value. Therefore, the conclusion is that the semiconductor is p-type. Okay. Now let's discuss this derivation. This derivation, Rajiv. I will already share in this PDF. This is a derivation. You should remember this expression. Okay. I will already share. I've already discussed in the video. The recording will be shared on my YouTube channel, and also the PDF will be shared. But the theoretical question I'm just discussing again, just for the sake as we have joined later. So let's discuss one more question of this. So this question is there. Do you know why silicon and gallium arsenides are the preferred material for solar cells? Any idea?
There are many reasons, but what is the
What?
cost of
Sorry, could you repeat?
audit?
Your voice is breaking. You type in a chat box, Rajiv. It will be good.
Let me change my position. Now I am audible.
Yeah, yeah, you're audible.
See, semiconductor silicon is one of the very good semiconductor
Absolutely.
uh, in which the effect of the photon impact has the we can say it's most maximum as of now as compared to the other semiconductors available economically and technically. But this is the one of the main reason. But here, what you are referring, I am not able to
Okay,
catch up.
so like we're talking about solar cells. First of all, why I'm asking these questions, I think I included this question to enhance the thinking capability to design the material. So my point is this, that we know silicon is a good semiconductor, gallium arsenide is there, but if that is the case, all the semiconductors should be considered for making solar cell. Why silicon only? What is so special in silicon? Like we have this carbon family, right? Carbon, silicon, germanium, and then lead and tin is also there. Although they are not semiconductors, but they are materials like lead sulfide or cadmium telluride. Why they are not used as materials for solar cells?
Technically, I'm not exactly confident what to reply you, but so far as photovoltaic cells are concerned, we need a material which is hugely available in for manufacturing these solar modules. So silicon is because it is made from the you can say dust rather. Uh, it is available in ground, and extraction of that thing is not that costly. I'm talking of the commercial terms,
Hmm.
and although the process of converting into the ingots is not that easy, there are very few manufacturers in the world which are doing so. However, same might be applicable for other semiconductors as well, but I think it is available in abundance compared
No,
to
there
others.
are other semiconductors also which are available in abundance. And if that is the
Yeah.
case, that's why I framed the question like this. If you see the question, I have used two, silica and gallium arsenide. So if you're talking about abundance, you're absolutely right, Rajiv. You are saying it very well on the basis of commercialization. But why gallium arsenide also? Like I want to know the chemistry and the physics aspects of it. Can you talk in terms of band gap?
No, I'm not aware about that.
Okay, okay. So that is why I put it this question. Okay. So let's see the answer. Okay, so this plot you have seen the solar radiation spectrum, where this is a plot in between solar irradiance and the H nu, and this has a maxima at around 1.5 electron volt. Okay, Rajiv, are you hearing me? There is a
Yes,
plot.
I'm getting,
Yeah,
I'm getting.
so the maxima is around 1.5 electron volt. Now, for photo excitation, we should have the H nu, which is greater than the band gap. Then only the electron can move in between valence band and conduction band, right? So, the semiconductor with a band gap 1.5 electron volt or lower is likely to give better solar conversion efficiency because the maxima is at here. Okay, so silicon has a band gap around 1.5 electron volt, while gallium arsenide it is 1.53 electron volt. In fact, gallium arsenide is better than silicon. You must be surprised to know, although it has a wider band gap because of its higher absorption coefficient. Not only the band gap, but the absorption coefficient, the drift current, the electron hole carrier mobility, everything matters. Now, there could be another questions that if we choose materials like cadmium sulfide or CDSE, acha Rajiv, what do you do? Like, what are you pursuing right now?
I'm pursuing PhD.
Yeah. So you have you read any paper related to solar cell, quantum dot, dye synthesized solar cells?
I have, but my study is not going for technology study. It
Okay.
is more into the implementation.
Okay, so just for increasing your knowledge, let me tell you that mostly material like CDS, CDSC, they are very much commercialized into various devices. They have a band gap around 2.5 electron volt, but we can only use one component of this solar energy for the conversion. Okay, and also there are materials which are having very less band gap like zero point 0.4 electron volt, which satisfy the condition as nu is greater than band gap, but why we do not use them? Why? Because the solar radiation will be absorbed on the top layer of the solar cell and will not reach in or near the depletion region. For effective electron hole separation due to the junction field, we want the photo generation to occur in the junction region only. Okay, Rajiv, as you have not read the solar cell part, let me increase your knowledge. Just for the sake, let's consider a general architecture of a an NIP solar cell. Okay. Okay. So can you see this figure, Rajiv?
Yes, yes.
Yeah. So here I'm talking about perovskite solar cell. Perovskite is a material in which a lot of research going on. Now they can be NIP type, they can be PIN type, reverse like NIP, PIN. So it's there we use a hole transport material and electron transport material. Now this material is there which is actually responsible for all the gain, like what should be the bend alignment, how this electron and hole should create a circle so that more and more efficiency should be there, how this stability of this material should be modulated and channelized. We're talking about this material now. If I talk about perovskite, and if we talk about the normal dye sensitized solar cell, let's see this is like how this is there, this is there where our material is. Now how do we choose this material? In order to choose this material, I put in this question that the band gap should satisfy a particular condition, and that condition is not the only condition that should be taken into account. We should also worry about the absorption coefficient and also other factors. So not every material which has lesser band gap or high absorption coefficients will be good for use as solar cell. And solar cell are different from LEDs and other devices. Like it's just for increasing your knowledge. Although as you are taking this course, just for increasing your knowledge. Okay, so there are numericals which you will see in the video already. Acha, Rajiv, which of the following dopant do you think are not suitable for making an extrinsic semiconductor amongst them? Arsenic, antimony, copper, and indium.
Which of the following dopant are not suitable for making acid? I think it is antimony.
Okay.
No, no, copper, copper.
Yes.
Ah.
And only copper.
Yeah, arsenic and indium are there already.
Good.
Mm.
Indium is there.
Pardon?
Indium is there. Indium.
I think, I think with some mixing with other material, indium is there.
Yeah, mixing, but in the pure form, is it there?
No, not in pure form. Probably. Okay, there are multiple dopants. So S is there. I think apart from arsenic, maybe all of them are not suitable.
Yeah, antimony is there. Okay, antimony is suitable. Copper and indium are not suitable. Acha, you know the difference between intrinsic and extrinsic very well, right?
Uh, can you explain me once more?
Yeah. Okay. We know that intrinsic and extrinsic semiconductor. I have tried to make tell the difference on basis of six parameters. The first is the basis of impurity, and these extrinsic are further classified as N or P type. Okay, Ravi. Rajiv, sorry, Rajiv. These extrinsic are further classified as N type and P type. So if we take a difference between intrinsic and extrinsic, they are the pure forms of semiconductors, but they are the semiconductors which are made by adding impurities, and we can modulate the conductivity in these semiconductors because we are doing impurity. Impurity adding means we are doping something amongst them. So when we are doping something, we are playing with the number of electron and holes, and the electrical conductivity of these material also depend on the amount of doped impurity as well as temperature, and the Fermi level also shift to the valence band or the conduction band on the basis of the dopant conduction and valence maxima. So examples are silicon and germanium crystals with impurity atoms of asbestos, antimony, or phosphorus, or indium, boron, aluminium, etc. They are the elements which are generally classified as impurity addition. But in this question, the answer that is there is this. You can see question number 5 is this: copper and indium. Although indium is used in mixed form, but it's not considered. Copper we don't consider, but the answer of this question is C and D. Copper and indium. Generally we don't do. And you know when we dope something, it is N type or P type on the basis of donor impurity. If the donor impurity is contributing the electron, that means this is N type. It is if it is creating a hole, that means we are doping something which is trivalent, and we are doping something which is pentavalent. When this is pentavalent, then this is create an electron, which it makes it N type, and when we are doping something which creates a hole, that is making it P type. Okay, and mostly uh, preferred are silicon and germanium only, but on the basis of like what kind of extrinsic semiconductor we are trying to make, N type or P type, we choose our material. But your answer was right: copper. Indium, yeah, indium is a little bit like some people use it, some people don't use it, but the answer is copper and indium. But copper generally is not suitable for making an extrinsic semiconductor. Do you get the answer, Rajiv?
Yes, yes. Thank you. Got it.
Okay, so
What is this Fermi? What is Fermi level?
great. Okay, Fermi level energy. Basically, see, when there is a conduction band and a valence band, let me show you this figure. Okay, when there is a conduction band and a valence band, okay, so when we dope something or when we change something in the material, the intrinsic property of the material, then there is the conduction band can go up or down, and the valence band can go up and down depending on the doping and the electric field that is generating inside the semiconductor due to doping. Okay, now there is a Fermi level uh, which comes into the picture because of this doping. That means from there, like when electrons are hopping from the valence band to the conduction band, suppose they are not able to go to the conduction band, till where they can go. So there is a like imaginary line in this which is known as Fermi level energy, and this Fermi level energy is further studied very well. If you see this figure that I have already told, uh, yeah, here, if you see this figure, if you see the conduction band and the valence band, so on the basis of number of electron, the conduction and the valence bands are designed, and this energy gap is called the energy gap. Here somewhere in mid there must be some different energy state which will be present, and the collection of these different energy state will result in the formation of a energy level which is known as Fermi level. Are you getting me?
Now, this diagram is little bit difficult to understand because the previous one I was getting it, but now shifted to this one. So
Okay,
what are these blue lines? Can you tell me?
okay, which lines?
The blue lines, the
Oh,
graph.
they are the different states. Okay, we have read this principal quantum number and azimuthal quantum number, right? Now this balance band and conduction band, how does it come into the picture? The balance band and conduction band is nothing but density. Like it's not a something realistic. Like some band is there which is having the electrons. It's like there is a density of electrons. Okay, now balance band is something where there is high density of electrons. That means it is composed of the orbitals which have filled electrons. Okay, but there could be orbitals which are not filled but still present in an atom, right? Which are responsible for the formation of conduction band. And so this is like the different electron states which are responsible for formation of conduction and valence band. This is are you able to understand or not?
Yeah, these two n state and six n state are the two different
Yeah,
state of.
exactly, exactly. Because of this different in the azimuthal quantum number, if you remember, two p, three p, one s, two s, two p, three s, three p, four s, three d. So two s and two p orbital. This outermost electron is four, and then this crystal becomes four n, and then this with two s plus six p it will become eight. Then the crystal becomes six n. These are the two n states, and the gap in between them is called the energy gap. I have taken this picture from chapter number 14 of our NCRT textbook. If you're not able to understand, you go through this. You read this, and if you are still not able to understand, you write me a mail. I'll tell you the. But I have tried to explain the concept of conduction and valence band on the basis of the density of states of electrons. Like you don't consider like there is something like this, so that, and you know what is a Fermi level. If from here only we say about the concept of the Fermi level, this is the highest energy level that an electron can occupy at an absolute zero temperature also. Are you getting me?
Highest level of what?
Like this is the highest energy level that an electron can occupy at the absolute zero temperature also. Like this is not a very realistic concept, but there there occurs just a minute, there occurs a level of energy. If I am showing you this, my laptop is hanging, just a minute, Rajiv.
Okay.
Oh god, again this issue is happening. It is happening. Yeah. Where have I put it, that picture? Yeah, here it is. Yeah, this is the figure that I was talking about. This is a conduction band, this is a valence band, this is an intrinsic electric field. This is the Fermi level that is coming into the picture. This is going down, this is going up, and there is in between them there is a energy level where you can find the electron even at a lower temperature. Like even though you're not providing any bias, no, but there will be certain electrons which are present here. This is called a Fermi level, and the energy this is corresponding to this level is called a Fermi level energy. So we define the Fermi level as the highest energy level that an electron can occupy at even at absolute zero temperature. Like you can find the electron here even when there is no separate external stimuli you are giving. Are you getting me? You have a balanced band energy, you have a conduction band energy which is confined, but also still you can find some electron above it, even though you're not providing any temperature, any pressure, any external stimuli. What is that energy level? That is called a Fermi level, which is
Okay.
yeah.
So what happens in case of the silicon and the other arsenic or other semiconductor? Why silicon is more preferable so far as this Fermi level is concerned?
Yeah, because you can find the electrons in the Fermi level even at lower temperatures, right? And the
Okay.
Fermi level lies near to the conduction band. Now this position of the Fermi level also matters on the basis of doping that you are doing. So this Fermi level varies the kind of doping that you are doing into the material. Let me show you this question that I have designed. I don't know what is happening, Rajiv. My laptop is little hanging. Okay, this question was there. So in a PN junction, how does the built-in potential change with temperature increases? And you can start by considering that the Venn diagram and expected evolution of the Fermi level with temperature. This was the question, and the answer was this. The answer that I have put it into this is this. We know that this, this is a equation which is EF minus EB for the P side and EC minus EF for the N side. Now, just for the sake, we know that the Fermi level shift towards the center of the gap when the temperature increases. Just for the understanding, when the temperature is increasing, the Fermi level is shifting towards the center of the gap. Okay, so they both, that is the EF minus EB P side and EC minus EF N side, will increase with the temperature. Consequently, the BBI value of the junction will be reduced. That means the electric field will be reduced. Now, in layman language, let me explain it to you. You have a conduction band, you have a valence band, there will be a Fermi level. Now this Fermi level will shift on the basis of doping, and this shifting of Fermi level defines the production of the bias electric field inside these bands, this whole electron carrier dynamics. Now, due to this shifting, which shifting is occurring due to the temperature, pressure, or some external stimuli, we get more efficiency. Like we play with other factors. Like if we are doping something, more electrons, then this Fermi level can shift towards more conduction band. If we are changing some temperature, pressure, this Fermi level can shift towards more balance band. Now what property do we need from the material? Suppose we are designing some material, we want it to be blue emitting. Now we know the energy BIBGYOR. Now, how do we do the doping? How much percent of doping can give this blue emission? How much percent of doping can give this green emission? Which decide it? We cannot just go and dope something like 10%, 20%, 30%. There need to be a proper basic concept. So each material has some Fermi level, and now we see when we are doping something how this Fermi level is changing. Depending on this, we choose what material to dope and in which material we dope. So every material has some Fermi level energy. Are you getting me? Although this is not a experimental concept, but yeah, there is a Fermi level that exists where you can find electron even at 0 Kelvin, and these electrons are the electrons which are available, which can actually decide the properties of your device. Which this concept is very much important for devices like LED, transistors, photodetectors, solar cells. These, so we need to know the Fermi level energy. Suppose we want to use the electron for doing photocatalysis reaction. Okay, Rajiv. Now photocatalysis means we are using light, we are exciting a material in which the electron is going from the valence band to the conduction band, and we are using that electron for reducing something. Now suppose we are exciting light, UV light, blue light, green light, orange light. Now which light will give the electrons more efficiently, and it will not jump over, like it will not show tunneling, and it will show efficiency, and also it will not degrade the compound. How will we decide it? For these factors we need to know the concept of Fermi level energy. So like this is more like more correlated with density of states, DFTs. In computational we know DFT. From DFT we calculate density of a state, P density of state. From there this concept is much more related, but every material has a Fermi level energy. Are you getting me?
Okay, fine. But one more thing which is arising in my mind is, what is the pressure how you define the pressure in this particular case? You said
Okay.
temperature and pressure affects Fermi level.
Yeah, yeah, it do.
So what is the pressure here? How do you define pressure?
No, here it was temperature. Here I was changing the temperature. Okay. Yeah.
Okay.
Here, uh, uh, like how the evolution of Fermi level will change with temperature. Now, the external stimuli could be temperature also and could be pressure also, right? So, okay, let me tell you something. There are certain papers which talks about the change in the crystal structure on the pressure regulation. What they are doing, they are applying pressure from 100 millibar to 200 millibar to 300 millibar. Now what people are observing that at 100 millibar it is showing some other space group. In the same compound at some different temperature is showing some different space group. That is, the orientation of the atoms are changing, the orientation of the electrons are changing. Now why this is happening? This is happening due to the electrons. And when people are taking in situ absorption or in situ PL spectra in presence of pressure, they are seeing the change in the PL intensity and a shift also in the peak. Now for what this peak is responsible for, that means the Fermi level is also changing due to pressure, right?
I'm still unable to understand what type of pressure it is. It is a physical pressure or some
No,
pressure due
this is
to.
like external stimuli. External stimuli pressure means, like, suppose you create a vacuum. Suppose you are doing some measurement, you create a vacuum. Okay. Now there is
Mhm.
actual pressure already present inside. Like suppose you're creating a partial vacuum. Now you're creating a full vacuum. You tell me, will there be some pressure inside a partial vacuum? Yes, definitely. But when this is a full vacuum, it will not be that much, right? You agree, Rajiv?
Yes.
Yeah, so I'm talking about
So it's
that.
an external force basically.
Absolutely right.
Mm.
Don't create it like this that I am pressing something, this type of pressure I'm giving. No, I'm talking about external stimuli. I'm changing the pressure in the environment. Okay,
So
that is.
this particular property, suppose this solar module is manufactured
Hmm.
using silicon,
Hmm.
then also this property of pressure plays an important role throughout the
That
life of the solar
that
module.
that I don't know, Rajiv. I think I need to study for that. But I think yes, pressure creates a role. But generally, what these solar cells are kept in the open environment, and at normal temperature and pressure, like this STE condition have na, that is standard temperature and pressure. We generally have pressure what 760 of HD outside. In these condition, I think from 760 to a very high value, the materials shows like stable condition. The silicon materials, they are very stable, but there are certain materials which are not stable in these pressure domains also. So this is a material intrinsic property. What material is showing change in the Fermi level on the, like, okay, let me tell you something very interesting now, so that you can correlate. There is a concept called chromism. Okay, Raji, what is
Mm.
chromism? Chromism can be thermochromism, chromism can be electrochromism. Now what happens, this COVID was going on now. So in COVID what people were doing, acha, now COVID vaccine need to be kept at a particular temperature. Now you cannot keep the thermometer and keep on checking the temperature every time. So there
Mm.
comes the concept of thermochromism. That means there are certain materials which shows different kind of luminescence at different temperature. Okay, but at a particular pressure, you need to make a pressure constant. So what people are doing, they made certain devices where they kept the pressure constant, and they put it that material on the tape of the vials. Now what was happening, they suppose they have to be kept as minus 20 degrees centigrade, and the temperature has gone to 0 degrees centigrade. The material was getting from orange to blue, the tape is showing blue. So you cannot keep on checking the thermometer every time, but the color change, you can simply see, oh yeah, temperature is increasing, we need to decrease the temperature. You decrease the temperature. So why this color change is happening? What is responsible for this change in electron carrier dynamics? That is external stimuli. And what are the external stimuli? The variables. What are the variables? The pressure, the temperature, all these factors. Are you getting me? But it is not necessary that for a certain material, if pressure is creating some issue, for other material it also should create some issue. For example, I'm working on a material which is stable till 500 degrees centigrade. It has a water crystallization, and the water goes at around 200 to 250 degrees centigrade when I see it in TGA. And after that, till 500 degrees centigrade, there is no change in the phase, no change in the UV, no change in the PL. Even at different pressures, it does not show any change in in the XRD. That means my material is quite stable.
Okay, but you know why I'm asking you, because once the model is manufactured,
Hmm.
the property which is affecting is temperature. The standard test condition only spells about the temperature and the per square, the solar radiation and the air mass ratio, but it is not specifying any pressure details or specification to this
Ah,
thing.
now I get it.
But throughout the life,
You're saying it. Okay, okay. Let me tell you one thing. It is just like you're absolutely right. Now I understand what you're trying to say. Let me tell you like this. Um, mm, have you read these Boyle's law, Charles law, and these laws?
yes, but not remembering right now.
Yeah, yeah. So there was a law which creates a relation between pressure and temperature. Now that law created a relation between pressure and temperature, keeping the volume constant. Okay, and then there was a law which created a relation between volume and temperature, keeping that pressure constant. So pressure, volume, and temperature, they three are codependent terms. And the gas equation shows P1 V1 over T1 equal to P2 V2 over T2. Okay, now I'm not talking. Okay, so like, let me tell you in these terms. You know, strain and stress.
Yes.
Yeah, okay. So every material has some strain or stress, right?
Mm, under some condition, yes.
Yeah. Okay. So if this strain and stress is there, and we are can we change this strain and stress by some modifications, like some instrumental this, like suppose we are creating pressure or something, or we are trying to put some strain. Can we put some, like suppose we are doping something, and in the lattice the bond angle is changing. That means some strain or stress is happening.
Yes.
Yes. Now isn't it a kind of pressure?
Yes.
Yes. Now you get it what I mean.
No, I got your point, but my question was that once it is form a permanent state, now there is no change in the physical form of that particular semiconductor.
Hmm.
Then throughout the life, when it is producing these solar electricity generation,
Hmm.
uh, even during that period, also this pressure has some impact on generation.
Mm,
And
yeah, it
if it is
has.
changing the property of the semiconductor.
Yeah, it can, but I'm telling you now, we are commercializing a material which are stable till a very high value of pressure. Okay, so the material which are like commercialized, they are quite stable at very till very high pressure conditions. So they do not show any condition, any problem. Like if you see if you go to Mount Everest, and if you climb the Mount Everest, and you can see that the way your phone is getting dead on the earth, and at 8,000 feet level high, the rate will be different, but it is very like not very observable, because this is not a very major factor which is changing it. We have to change the pressure a lot in order to make some observable changes, because the material which are being commercialized, they are generally stable. Are you getting me? So people
Mm.
generally neglected temperature is a very observable factor, but yeah, it creates difference.
Is there any research on this thing? Just a loud
Yeah,
thought
yeah,
coming in my mind.
definitely. I can send you some papers.
Because see, I am in this field since last 35 years, so I'm more worried about after installation generation. When see, you can say that this particular cell has a 30% efficiency.
Hmm.
You can enhance to 100% also.
Hmm.
But how does this work in the environment where it is installed? That efficiency is the benchmark, but what is the real output is the revenue generation factor of that particular solar projects. So we have been focusing only on temperature and to some extent air mass ratio, which is still not catered precisely during the operation of the system.
No,
Uh,
there are papers which talks about the effect of pressure, which are changing the Fermi energy and creating disorder in the materials. I can tell you, but I have no idea. Like people have tried to implement it in devices, but yeah, there are literature present. I can tell you. the pressure induced changes in electronic structure and the density of state and the phase transition and how this phase transition is changing the optoelectronic and the photophysics and how these optoelectronic and photophysics is devising the IV curve, that the current that is there and all these factors. But yeah, I know there is no pressure term in the equation. That's what you're talking about, right?
I know, Mr. Shrestha, I'm still in a dilemma, and it's a big question that all the research on the solar photovoltaic cells and modules are within the campus, under the roof. But I think there are very few research which are happening in the field. What is the effect of all these factors? Even the what is the status of the silicon cell or even the other cell
Hmm.
after say 5 years or 6 years? It is just during the manufacturing status a projection is made that it is the life is 25
Okay, let
years.
me tell you one thing. You know what, Rajiv? You must be knowing you are in this field for a very long time. Uh, okay, so generally we are making these solar cells or devices in particular conditions and situations, right? I'm not able to admit her. I don't know what is the issue. So generally we are doing it at a particular condition. Like we are suppose we are manufacturing a solar cell inside the globe box. There we keep the oxygen level maintained. We keep the inert environment, and also we keep a certain pressure. Okay. Now when we commercialize the same material, suppose we reported a material that is showing 33% efficiency inside the globe box, but in realistic condition when it comes it shows 20% efficiency. Inside the globe box it is stable for 8 months, but in realistic condition we will see it is stable just for 2.5 months. Okay, so these are the parameters that are there. That is why that this is one of the major reasons why perovskite solar cells till date are not being able to replace the dye synthesized or the quantum dot solar cells, because of the stability in the realistic environment also. Are you getting me? And if as far as this question of yours is concerned, I have some literature. I'll also look some literature and I'll definitely try to mail you the answer. Could you write your email ID, Rajiv, in the chat box?
Okay.
Yeah. I don't know, I'm not able to admit her. What is the issue?
I can't help you out in this because you are the admin, so
Yeah. You write your email ID in the chat box.
I'm doing it.
Okay. Okay, Rajiv. So I'll try to make a short video and also PDF and I'll email this. Like your question is how this pressure is changing the Fermi levels and how this pressure, if this pressure is regulating the Fermi energy of the materials. So how this is depicting the overall efficiency of the devices, right?
Yes.
Okay, definitely. I'll answer your question.
Why I'm thinking on this thing because see in my I'm from Chhattisgarh basically,
Okay.
though I'm doing my PhD from Shulini University, Solan.
Hmm.
So we have got more than 1 lakh, more than 1 lakh off-grid solar systems
Hmm.
in Chhattisgarh system, which we are maintaining. The main task is how will you evaluate that this module is working efficiently or not. So we don't have pyrometer installed everywhere.
Hmm.
So as a thumb rule, we are maintaining it. But in due course of time, what is coming in my mind that we have to be more intrinsic and more precisely monitoring all these things.
Absolutely.
And now to this Fermi level, this word was not well known to me. This is concerned then our further details, though it is not in our scope officially, it is not, but we have to go in depth and understand the property of the cell which are there in the solar module with
Exactly.
respect to the time. So that
Exactly.
study has to be taken up.
No,
So
definitely. That's very interesting, and you're absolutely right. Commercialized people have not thought a lot into this domain, but yeah, it is one of the factors that can really change something. I feel so. I'll try to answer your question, Rajiv. Okay.
right, sir. So
Okay.
what are you doing right now, Shrestha?
Okay, so like I am working on this perovskite solar cells, and I use this perovskite materials. I make the nano. I make the bulk of them, and I try to find applications like LEDs, solar cells, photo detectors, and also right now I have started working on X-ray detection. Okay, like hard radiation detection. Now people are trying to detect hard radiation like X-ray, gamma rays, all these things, so that like suppose some people are carrying something like something in the powder form, some radioactive material that can be detected. Okay, and also some like like magnified and colorful pictures of X-rays are coming. This quality is getting increased, so we need to have some materials which are doing it. So I'm working on that, and along with that I also try to make some nanomaterials to find the application in the biological domains like multimodal bacteria killing and this cancer. And our research group also work on electrochemistry, that is water splitting, CO2 reduction, and batteries. Okay,
And
so
how have you included this PERC, that is passivated emitter and rear cell technology in the solar module?
what?
PERC, passivated emitter and rear cell. Nowadays, the solar module
Hmm.
are being manufactured with PERC technology.
Okay.
It seems as more efficiently. It is more in PERC technology. PERC.
Oh, I didn't know it. Like what we do, we generally make it on FTOs, and then we club the FTOs. We do the coating, gold, and all. Then we club it, and then we do the measurement in the solar simulator, and we plot some IV curve, small Schottky curve, and all this, and then we publish the papers. On commercialized level, how they are being manufactured, I have a little less idea. But yeah, I'll try to look into it. PERC,
No, on
PERC.
company is being manufactured globally. And
Okay,
it is envisaged that 2020 almost all the solar module will be PERC.
okay.
I have my chat box.
Okay, I mean, I have no idea about it actually, to be honest.
You go through it, it will be interesting for you also
No, no,
to add it.
definitely, definitely. We are here for learning. You tell me something new, I'll tell you something new. This is how the research and the field and the science flourish, na? I'll definitely look into it. The PERT model, how the solar cells are getting manufactured nowadays. I'll look into it because we are generally into academia, na. So we like I am into academia, and I am not hardcore working on solar cells. So probably I don't have this idea. I am generally working on designing the materials. Like my work is to design new materials and study their properties. So
Okay.
application wise I am little less known, but yeah, I'll try to read it.
So basically, where you end, I start from there.
Yeah, exactly, that is the point. We can connect ourselves.
Yes. So, okay. So you can just send me the link because I am unable to find the link to see all the lectures. And suppose I have forgot something, I go through the YouTube link. Your
Yeah,
YouTube link where this lecture will be available.
I shared actually. I don't know. I'm not able to use a chat box and nothing in this. Something is happening.
So you can share me on email, my
Yeah,
email ID.
your ID was rajivgyani@gmail.com, right? I'm not able to. I'm clicking on it, but nothing is happening. You could you send me a hi on my email ID, Rajiv?
Your email ID.
Hmm.
Oh, what is your email ID? Tell me.
SD19IP
S
G.
G.
Okay. Now I think it will work. Just a minute. Yeah, now it is working. My ID is SG19IP011 @isaacool.ac.in. Now I have got your ID too, Rajiv Gyani, and I am sharing my YouTube channel video also. So this is the link. Although these all are available there, this is a link of the Google Sheet in which all the TAship classes are being shared. You can see, and this is my YouTube channel link. All of we have three TAs here. The two are from this solar background only. I am from the material background. This is my YouTube channel. You can find all the TAship discussions of all the assignments in this drive. Like all the backup videos and the YouTube videos are being shared here. Along with that, the videos are also shared in YouTube, and you also have the PDF solution and the PPT that we present here every week. It is updated. So in case you miss, or in case you want to see again, in case we are not able to satisfy any of your doubts, you can send us email, or you can send us all an email, or you can even CC the professor. You can do that. Okay, Rajiv.
Means Ashish Garg.
Yeah, Ashish Kar from IT Control.
So thank you, Suresh. Thank you very much.
Okay, thank you. Nice to talk to you, Rajiv. See you.
Bye bye.
Bye.
See you.